Hey everyone! Today I'll be explaining question 59 from the Unit 2 problem set. Alright, so a football is thrown across the field so that its height, in meters, is modeled by the function h at t equals negative 4.9 t squared plus 19.6 t, where t is measured in seconds and where the domain of t is from 0 to 4 seconds. Part A. Determine an expression for the h prime at t and use it to determine h prime at 3. Explain the meaning of your answer in context and with correct units. Now, h prime at t is the first derivative of h at t, our original function. So to determine h prime at t, we need to differentiate our original displacement function using the power rule. And once we have our derived equation over here, we can substitute the value of 3 for t to evaluate our answer, which is negative 9.8 meters per second. Now, knowing that h at t is the equation of the football's displacement, our original equation, we know that h prime at t is the equation of the football's velocity, because velocity is the first derivative of displacement. Remember, velocity equals change in displacement over change in time, or simply, velocity is the rate of change of displacement, measured in meters per second. So when we substitute the value of 3 seconds in the h prime at t function, we're determining the velocity of the football at 3 seconds, which is negative 9.8 meters per second. Part B. The second derivative of a function can be found by differentiating the first derivative. Determine h double prime at t and use it to determine h double prime at 3. Explain the meaning of your answer in context and with correct units. Now, h double prime at t is the first derivative of h prime at t. So to determine h double prime at t, we need to differentiate our velocity equation using the power rule again to get a constant function of negative 9.8 meters per second squared. Now, this is the equation of the football's acceleration. And remember, acceleration equals the change in velocity over change in time, or simply the rate of change of velocity, which is meters per second, or meters per second squared. Now, as you notice, substituting the value of 3 for t doesn't apply for this equation because this is a constant horizontal equation, meaning that for any t value from those 0 to 4 seconds, the acceleration of our football will be a constant negative 9.8 meters per second squared. Alright, part C requires us to sketch a graph of the displacement, velocity, and acceleration of our football. And below I included some essential steps to sketching, and I'll be guiding you through how to sketch each function right now. Alright, first you actually want to start with your acceleration function because this function has the least amount of features considering that it has the simplest equation. So the first step is actually writing the equation on the right side of your grid, which is just going to make things a lot easier. Next, you want to calculate your y and x intercepts and carefully label them on the graph. Labeling these features is actually very crucial in determining the features of other graphs, and I'll show you that as we move up. Alright, so here is my labeled line. As you can see, it is just a constant horizontal line with a negative value of negative 9.8 meters per second squared, and the only key feature is the y-intercept over here. It is very imperative that you label your axes as well as your sketched line with any key features for all of the graphs that we're about to sketch. Alright, now we can sketch the velocity function. Again, I included the equation of the function in the right corner, and I determined the y and x intercepts, and I labeled them accordingly. So in this case, you can see some dotted lines which connect my velocity and my displacement graph, because this x-intercept in my velocity graph actually helps me determine the turning point of my displacement graph. So let's look at the connection made here. Here in the velocity versus time graph, at 2 seconds, the velocity values go from being positive to negative. And this means that the object has changed directions. Anytime we see a change in the sign of the velocity, we know that the object has changed directions. And in our displacement versus time graph, we can actually see the exact trajectory or the pathway of our ball. So from 0 to 2 seconds, the ball is moving away from the ground into the sky, and at 2 seconds, it stops momentarily where the velocity is 0, as you can see here, and that the ball begins moving towards the ground. So not only has the velocity of the ball reached 0 at this point, but we're also turning directions. That's why anytime we switch planes in this velocity versus time graph, it means we've changed direction. So knowing the x value of this x-intercept can help us calculate the vertex in our displacement versus time graph. And we can do that by substituting the value of 2 in our displacement equation to evaluate 19.6 meters. All right, again, I'm going to write the equation in the top corner. As you can see, it was really easy to just calculate that vertex. And I'm also going to compute for my y and x intercepts and sketch the equation accordingly. All right, so now that we have our 3 graphs sketched, we can answer the following questions about this scenario. Part D, when are each of these values positive and when are they negative? So we know that our x domain is going to be entirely positive, so from those 0 to 4 seconds. So this question is essentially asking us to look at when the y values of each function are positive. So our displacement function is entirely positive, as you can see, from those 0 to 4 seconds. All y values are in the positive plane, positive y plane. So that's why we can express that for h at t, we have an entirely positive function. And I'm using these round brackets because if this function were to extend in the negative y plane, we would see that change in signs of the y values. So at those 0 and those 4 seconds, or any other seconds on this horizontal line, we're not sure whether the equation is positive or negative. So we need to use our round brackets. Now, for the velocity function, we can see that from 0 to 2 seconds, our velocity values are positive, and that from 2 seconds, we're changing the sign of my velocity, which is now negative. And that is why at those 2 seconds, we're using the round brackets, as you can see here. But we know for certainty that at 0 seconds, my velocity value is initially positive, and that at 4 seconds, our velocity value is finally negative. Now, for the acceleration function, we know that it is entirely negative for the entirety of the domain. So we can just express with certainty that from those 0 to 4 seconds, we have a negative function. All right, part E. When is the football moving towards the ground and when is it moving away from the ground? I briefly discussed this previously, but we can look at whether the ball is moving towards or away from the ground based on the velocity versus time graph or the displacement versus time graph. So let's begin here first. So when we kick the ball up, so picture a little guy kicking this ball, we're kicking it from the ground into the air. So it is moving away from the ground. And from those 0 to 2 seconds, it is doing exactly that until it reaches the 2-second mark where the ball pauses and then switches direction and starts falling back towards the ground under the influence of gravity. And this can be represented in the velocity versus time graph when from 0 to 2 seconds, the velocity values are positive but decreasing until they eventually reach 0, and then they start increasing from 2 to 4 seconds as they're moving towards the ground. So this can be expressed here where at 2 seconds, we know our ball is changing directions from towards or away, from away to towards. So we're using our round brackets, and then at 4 seconds and at 0 seconds, we're certain that the ball is moving towards the ground and that it is moving away from the ground. So we can use our round brackets. All right, part F. Determine the impact velocity of the ball. Now, impact velocity is simply the velocity of the football when it hits the ground. This is literally the ball's impact on the ground. So we know from our displacement versus time graph that the ball hits the ground at 4 seconds because this is our x-intercept, right? The ball starts from the ground, travels a distance, and it reaches back to the ground again. So to determine the impact velocity, we simply need to substitute this time of 4 seconds in our velocity equation. So I did that here using my derived equation to get a value of negative 19.6 meters per second. Now you notice that the value of the velocity is negative because this is the impact velocity. It has reached the ground. It is moving towards the ground. So that is my direction in this case. It is negative because the initial direction was moving away from the ground when we kick the ball up into the sky. So when it reaches back to the ground, it is a negative velocity because we've switched directions. All right, part G. When is the football speeding up and slowing down? Now, if you recall from the lesson, to determine when an object is speeding up or slowing down, we need to compare the velocity and the acceleration signs from those timings. So from 0 to 2 seconds, we have positive velocity values. But from 0 to 2 seconds, we have negative acceleration values, which means that the signs of the velocity and acceleration are different from those 0 to 2 seconds, right? When we kick the ball up, the acceleration is always dragging it downwards at those negative 9.8 meters per second squared, but our velocity values are upward because that is where we kick the ball. But as you notice, the ball slows down. It is slowing down over time until it reaches this value of 0 over here. So we know that from those 0 to 2 seconds, our ball is slowing down. Now, from 2 to 4 seconds, my velocity values are negative, right? And also, my acceleration value is still negative. And having the same velocity and acceleration signs, we can conclude that the ball is speeding up because the sign of the velocity aligns with the sign of the acceleration, right? They work together to cause the ball to speed up. All right, part H. What is the vertical displacement of the football over the 4 seconds? So we recall the displacement is the net change in position. So looking at our displacement versus time graph, we notice that the initial and the final positions of the ball are both at a vertical y-plane of 0, meaning that even though this ball has traveled a distance of up and down, its initial and final positions at those 0 and 4 seconds are both 0 meters, right? The ball hasn't moved vertically in totality, which is why we know that the vertical displacement of the ball is 0, right? Final position minus initial, so 0 minus 0 is 0. Part I. What is the vertical distance the football travels over the 4 seconds? So again, distance is the total length of the path traveled by the ball, so it is accounting for the entirety of the trajectory of the ball. So the ball flies 19.6 meters upwards until it reaches its apex and then falls 19.6 meters downwards. So adding those two values, we get our vertical distance of 39.2 meters over those 4 seconds. All right, that is the entirety of question 59 explained. Now, I suggest you solve question 61 from the problem set, and it is very similar in structure, except that the original displacement function is a cubic function instead of a quadratic function, so it includes some more complicated sketching, but that question will really reflect your understanding of the topics covered in this video, so I highly recommend doing it for homework. All right, I hope this helped, and as always, happy calculating. Thanks, guys.